At the very beginning of Chapter 5, they introduce a case study on page 287, and it says, many high schools now have drug testing programs for athletes. The main goal of these programs is to reduce the use of banned substances by students who play sports. It's not practical to test every athlete for drug use regularly. Instead, school administrators give drug tests to randomly selected student athletes at unannounced times during the school year. Students who test positive face serious consequences, including letters to their parents, required counseling, and suspension from athletic participation. Drug tests aren't perfect. Sometimes the tests say that athletes took a banned substance when they did not. This is known as a false positive. In other words, the test was positive, but the athlete actually didn't take a drug. Other times, drug tests say that the athletes are clean, they didn't take a drug, when they actually did take a banned substance. This is called a false negative. It failed to identify the drug they had taken. Then I'm going to skip over the question they ask here, and we're going to go to page 332, where they pick up on this problem again, and then ask a series of more specific questions. Suppose that 16% of the high school athletes in a large school district have taken a banned substance. Okay, so I'm going to say D for drug. D equals taken a banned substance. Drugs. Okay. And then we're going, and so it says, so the probability of D is equal to 0.16. So the probability of D complement, or not D, then would be 0.84. It says the drug test used by this district has a false positive rate of 5% and a false negative rate of 10%. Use what you've learned in this chapter to help answer the following questions about the district's drug testing program. Show your method clearly. Well, the first thing I'm going to do is make a tree diagram. And in a tree diagram, we start with the first thing, which did they take a drug or not? And we have that adding up to 100%. So we have 0.16 for the drug and 0.84 for no drug. Then we look at the false positives and false negatives. So here, either the person tested positive or they tested negative on both of these cases. Either the person tested positive for drugs or negative for drugs. So here's whether they took the drugs or not, whether they tested positive or not. So a false positive means that it said they took drugs when they didn't. So this is a case where they didn't take drugs, but they tested positive. That's 0.05. So the opposite of that then would be that they tested negative for the drug, which would be 0.95. A false negative means that it says they get a negative result on their test even though they did take drugs. So this would be 0.10, and then this would be 0.90. So if we multiply across, we have the probability of they took drugs and they have a positive test. That would be 0.16 times 0.90, and that turns out to be 0.144. Then the second is the probability that they took drugs and they tested negative. So that would be 0.16 times 0.10, which would be 0.016. Then the probability that they didn't take drugs but they tested positive would be multiplying 0.84 times 0.05. So probably no drugs, but they tested positive. That turns out to be 0.042. And then the probability that they didn't take drugs and they tested negative, which is a good thing, 0.84 times 0.95 is 0.798. So remember, we're always multiplying across for these probabilities. Now I want to show another way to organize the same information. So this is a tree. We can also organize it using a table. And I think I'll just do that in a different color. So in a table, what we would have is two different variables. We would have one where they took drugs or no drugs. and the other column is they tested positive or they tested negative. Now, when we do a table like this, what I like to do, instead of using percentages or probabilities, I like to pretend that there's actual people. So let's say, and I like to pick a big enough number so I end up with nice whole number. And so since these are all 3 decimal places here, when you multiply these, let's use 1,000 for our population. So let's say we have 1,000 students. So we start out with 16% take drugs and 84 don't. So 16% of 1,000 is 160, and 84% then would be the 840. Then 90% of those who take drugs test positive and 10% test negative. So let's start with the 10%. 10% of 160 would be 16. They test negative. The other, so 160 minus 16, that is 144. They test positive. That's 90% of 160. Notice those are the same numbers we're getting right here. 144 out of 1,000 would be 0.144, and 116 out of 1,000 would be 0.016. Then, given that they tested negative, or they didn't take drugs, they're going to test positive 5% of the time. Well, 10% of 840 would be 84, so 5% of it would be 42. So this would be 42, and the rest would, you guessed it, 798. So then when we add this together, we get 186 total who tested positive, and 16 plus 98 is 814 who tested negative. Okay, so this table gives us a lot of information too about the same situation. So what's the probability that a randomly chosen athlete tests positive for a banned substance? So I'm going to start by using a particular color for this. So let's make this red. Okay, so this is red. What's the probability that a randomly chosen athlete tests positive for a banned substance? Okay, so probability of positive. Well, probability of positive using the table would just be 186 over 1,000, or 0.186. The probability of positive given the tree, we would look for the 2 places where we have a positive. So it would be probability of a positive would be equal to 2 different cases. Drugs and positive, probability of D and plus. Probably need to make that and better. D and positive, D, let me start that again, do that again, D and positive plus probability of not D and positive. Not D and positive. I'm not doing very good with my symbols here. Not D, D complement, and positive, which would be 0.144 plus 0.042, which would be 0.186. So 2 different ways, both equally good, to find the answer to the first one. Okay, number 2. If 2 athletes are randomly selected, what's the probability that at least one of them tests positive? Okay, so we're not actually getting any new information here. We just have to think about that at least one thing. So I want you to remind you that probability of at least one means the probability of 1 or 2 of 2 randomly selected people. And realize that when you select 2 people and you said 1 out of 2, it could be the first one or it could be the second one. So you have several cases here that you're looking at. So because usually there's several cases you're looking at, it's easier to think about what's the probability of not getting any of them that test positive, and then just subtract that from 1. This is 1 minus the probability of, and I need to actually write this, at least one positive equals 1 minus the probability that neither are positive, which would be 1 minus the probability of both negative. Okay, so what is the probability that they are both negative? Assuming that it is independent, the tests are independent for each individual, and that makes sense. Assuming that each individual result for each person is independent of the other, we have two independent events. So we find out what's the probability that they test negative for the drug, and we multiply those times each other. So both negative would be 1 minus the probability of a negative times the probability of a negative. Okay, so we're going to multiply together those. Both negative would be probability of a negative times probability of negative. Well, probability that they tested negative would be 814 over 1,000, or 0.814. We could also get that by adding 0.016 times 0.798, which is basically what we're doing here. So 0.814. So this is 1 minus 0.814 times 0.814, or 0.814 squared, and that would be 0.337. So there's about a 33.7 chance that you would get at least one positive test from two randomly selected athletes. Okay, third problem. If a randomly chosen athlete tests positive, what's the probability that the student did not take a banned substance? Based on your answer, do you think that an athlete who tests positive should be suspended from athletic competition for a year? Why or why not? So this is a conditional probability. We're saying probability, what is the probability that given that they test positive, that they didn't take a banned substance? So probability that they didn't take a banned substance given that they have a positive test. Okay, so I'll kind of put this in parentheses. Given a positive test. All right, so we have to remember how we calculate something like this. So probability of D complement given positive is equal to the probability of D complement and positive divided by the probability of positive. So you do need to know, that's on your formula sheet, probability of A given B is the probability of A and B divided by the probability of B. So you don't have to have it memorized, but you do need to know how to use this. So using the tree diagram, probability of D complement and positive is 0.042. What is the probability of positive? We've already calculated that. That's 0.144 over plus 0.042. 0.1144 plus 0.042, or 0.042 over 0.186. And that turns out to be, let's see here, 0.226. Now, using the table for the same one, for number 3, the probability that they didn't take drugs given that they tested positive, so we look at all the positive tests, so we look at they didn't take drugs, so it's 42 out of 186. So using the table, the probability of D complement given positive is just 42 out of 186, which is 0.226. Now at this point you're probably seeing that figuring out probabilities from the table is actually easier than figuring them out from a tree diagram. Sometimes the tree diagram is more obvious to figure out from the given information. Sometimes the table is, but you can use them interchangeably, and if you can use whichever one you prefer. I think that making the table, it sometimes makes it easier to figure out the questions about the probability, but I think the tree diagram sometimes is initially easier to draw. So they both have their strengths and weaknesses. Okay, so let's look at the next. Oh, and then by the way, answering the question, do you think that an athlete who tests positive should be suspended from athletic competition for a year? I would say no, because the chance of a false positive, in other words, they tested positive, but they hadn't taken drugs, is quite high. It's over 22% of the positives are false positives. So I'm going to say no. 22% of positive tests are false. So I would say no, we shouldn't suspend athletes. I think that you should do some further investigation before you do any suspensions here. Okay, let's take a look then. I'm going to change this to black so that this matches, change my color here so it matches the rest of the problem. Okay, then the next question, let's go back to red again for number 4. If a randomly chosen athlete tests negative, what's the probability that the student took a banned substance? Okay, so we're saying probability that they actually took drugs given that they have a negative test. Oh, I was going to do that in red. Probability that they actually took drugs given that they have a negative test. Okay, so once again, let's look at both methods of doing this. So look at number 4 here. So we have probability of D given negative is probability of D and negative over probability of negative. So using the tree diagram, D and negative would be 0.016. Probability of negative would be 0.016 plus the other one where it's negative, which is 0.798. So total, that would be 0.016 over, let's see, I should have that written down somewhere. 0.016. I actually didn't add 0.814 or 0.019. Using a table, so this is using tree. Okay, so probability of D given negative using the table. If you go to the table, we just look at all the probabilities of negative results. 814, what's the probability they actually took drugs? 16 over 814, which is 0.019. This would be using the table. So once again, using the table is a lot simpler for some of these reverse conditional problems. Explain why it makes sense for the drug testing process to be designed so that this probability is less than the one you found in question 3. So it would make sense to me that there's a very high chance or very little chance of failing to detect the person who actually took drugs. Okay, so the false negatives are only almost about 2%. So only about 2% of the time do we fail to detect someone who is taking drugs. So if you're trying to catch the ones who are actually doing it, you want this probability to be low. But you have to recognize then the trade-off is that the probability of getting a false positive will be higher, and then you have to remember not to falsely accuse these false positives. Okay, one more. The district decides, need to delete this here. The district decides to immediately retest any athlete who tests positive. Assume that the results of an athlete's 2 tests are independent. Find the probability that a student who gets a positive result on both tests actually took a banned substance. Based on your answer, do you think that an athlete who tests positive twice should be suspended from athletic competition for a year? Why or why not? So basically we're going to look and see what happens, how often is that going to be false? Okay, so to test any, find the probability that a student who gets a positive result on both tests actually took drugs. So number 5 is saying, it's supposed to be blue. Number 5 is saying probability of taking drugs given 2 positive tests. So that's probability of drugs and 2 positive tests divided by the probability of 2 positive tests. Okay, so how do we find 2 positive tests, first of all. We kind of need to know that. What's the probability of 2 positive tests? So a positive test is going to come from 2 different sources. Or we can look here. What is a probability of a positive test? 186 over 1,000. So 180.816 is the probability of testing positive. So the probability of testing positive is 0.816 times 0.816. I decided I needed to back up and read my key on this one. This was one that, had I not looked at the key myself, I would not have known how to do. This is a very tricky one. So the probability of taking drugs and testing positive, okay, twice, is going to be probability that you took drugs, which is 0.16, and then the probability that you tested positive twice given that you took drugs. So that's going to be 0.9 and 0.9, because if you took drugs, the probability of a positive test is 0.9. So this would be 0.9, and then another positive test is 0.9. So basically this is saying drugs and positive tests given drugs and positive tests given drugs, because the testing positive and the drugs are not independent of each other. So this is something where the positive test is conditional on whether or not you took drugs. Now, what's the probability of 2 positive tests? Well, there's 2 ways to get 2 positive tests. There's either the probability that you took drugs and you got 2 positive tests, which is what we have here, or there's the probability that you didn't take drugs, 0.84, and you got 2 positive tests, which is 0.05. Okay, so that's really hard to see. Let's see if I can take all of this and kind of scoot it over and sort of clean it up on the bottom here. Very difficult to see that last little part. 0.05 times 0.05. In other words, the probability of getting 2 positive tests in a row is dependent on whether or not you took drugs. So either you took drugs and you got 2 positive in a row, or you didn't take drugs and you got 2 positive in a row. So together, the sum of that would be the probability of testing positive. And then the probability of taking drugs and getting 2 positive tests would be in the numerator. So when we multiply this out, and I'm kind of curious what these numbers turn out to be, so I'm gonna pause and do this on the calculator. Here's the probability of taking drugs and testing positive twice. Here's the probability of testing positive twice, 0.1317. So that was the denominator here. I was just checking to see if the overall probability of testing positive and then multiplied times itself would be the same as that, but it's not. So I could not have done it the way I was originally thinking about doing this problem. Now, what's the probability then of having taken drugs given that you've tested twice? Well, if I take the 0.1296 divided by 0.1317, I get about a 98.4% chance that if you test positive twice, you have taken drugs. Okay, so let's go back, and this turns out to be, grab this calculator screen. I think this would be helpful. And put it on here. Okay. So this is not the way to do it. So this turns out to be 0.1296 over 0.1317, which is 0.984. So the question asks, do you think an athlete who tests positive twice should be suspended from athletic competition for a year? There's a 98.4% chance that given 2 positive tests, they did actually take drugs. So probability of having taken drugs given 2 positive tests in a row is about 98.4%. Very likely to be a correct test, a correct decision. Now, so yes, I would say suspend, but allow appeal, because there still is a slight chance that this could be wrong, but most of the time this is going to be correct. This was a very challenging probability problem, particularly number 5. I'd say the other 4 problems you should be able to get. Number 5 was very challenging. This would be could be a problem on a test on an AP exam. Usually there's a few sections of some problems that are the ones that distinguish the really top students from the good, strong students, and this would be one of those types of questions. Sorry, I'm trying to turn this thing off and I'm having trouble getting my little symbol.